relevant application for decarbonization in the future of the energy sector. And you see that we are moving between temperatures, in most cases between temperatures of 800 to 1000 or more than 1000, 1400 degrees for the production of different kind of fuels, either through hybrid or 100% solar processes. So this means that in most of the interesting applications for decarbonization, we are really talking about important temperatures, probably in some cases beyond the conventional electrical solutions. Well, I suppose most of you are familiar with this diagram because it's commonly used in, I think, in 100% of the presentations from solar fuels. It's trying to summarize the different routes that you may establish to produce with solar concentration interesting products, either for storage of energy or for production of solar fuels. In some cases, what we are interested is in promoting the use of some reversible reactions that they should involve high enthalpy, so that we may, let's say, go to higher densities of stored energy. And this is one of the examples using typical metal oxide oxidation reduction as reversible as possible, so that we might use for many cycles. Or alternatively, in the case of solar fuels, we have two typical solutions. One of them is mainly thinking on decarbonization of existing processes, and in that respect, what we are trying is solarizing some of the steps in these processes, so that we might reduce the CO2 footprint. For example, in a typical gasification process, sometimes we need to gasify 1 kilo of carbon or coal. We might need sometimes even 1 kilo of additional coal for this purpose. So this means that if we can replace the part of the biomass or the fuel that is used to heat up the process, we can reduce as much as 50% the CO2 emissions. And finally, we have the solution of using also reversible reactions to try to produce some fuels. In the case, for example, of hydrogen, as you see here, normally we use typical metal oxide, for example, which is a quite simple chemistry, and we reduce thermally this metal oxide, releasing some oxygen at very high temperature, and then we undergo the second step, which is the oxidation of this material, for example, with steam, and try to regenerate the original material. Some nice friends, typical good guys, are, for example, Syria or mixed ferrites. In general, we try to avoid very complicated chemistries to favor as much as possible the cyclability of the process and the production of byproducts. I think yesterday already Wes mentioned about the Japanese approach, which is one of the clear ambitions. You know that Prime Minister of Japan last year in December 1 year ago, he promoted the first declaration of interministerial approach to create a program for introducing this kind of clean fuels in Japan. And this is the kind of the typical Japanese, very complicated, with many pathways and a lot of colors, but in general explains a little bit this kind of decarbonization with solar fuels or with clean fuels, where you have both pathways, the pathway of decarbonization of some conventional fuels, or in some cases the use of heat or solar electricity to produce clean hydrogen, and in some cases where you have to involve long-range transportation. People like the Japanese, what they promote is to create a number of carriers, And these are typical carriers proposed in these programs, like some hydrides. In this case, for example, in the middle of this slide, you see the proposal divisions from Chiyoda Corporation. That is in their project, together with Mitsubishi, is proposing to use a hydrogenation, dehydrogenation process involving methyl cyclohexane and toluene for the transportation, for example, from Brunei and Tokyo. Or what other projects, like the project using liquid hydrogen and the demonstration that is planned in 2020 for the Olympics. Also, there will be some kind of projects in this kind of demonstrations. But the problem, according to thermodynamics, when we go to these solutions, is the intensive demand of energy that we need to decompose the bond of oxygen and hydrogen. If you see the theoretical energy requirement in kilojoules per mole of hydrogen, you see the explanation why carbon-based bonds or hydrocarbons are much less intensive in terms of energy. So this means that, for example, in the case of reforming of methane, I suppose later on will be more expert people here explaining these processes, but in general, you need 6 times more energy to split the molecule of water than the energy that you need to split any other hydrocarbon-based bond. So that's the reason we need a very, very cheap solution, clean solution, but at the same time working at very high temperatures. So splitting water is not an easy job because we need very, very high temperatures, almost 3,000 degrees. So that's why at the end, in most of the CSP projects or in the concentrating solar community, we try to avoid this situation by using this kind of solutions where we introduce this thermochemical cycle solution with 2 steps. This is improving a little bit the conditions, but you will see in my presentation that still is not so easy. We are not requiring extremely high temperatures, but processes like this one based on Syria for the joint reduction of water and CO2, for example, it needs temperatures around 1,400, 1,500 degrees. See, this means also very high concentrations. So in any case, still I know that yesterday there were some comments on hydrogen and the opportunity, and it's true that this is still some way to go to this technology. But since you are talking in this meeting about the horizon 2030 and all the opportunities, I would like to specifically mention about the discussions in Spain, in my country, where also as all the member states in Europe, we are discussing the scenarios, and there is already a draft law proposed that is going to be apparently finalized by end of next month, and that should be presented to Brussels with the actions and the Spanish plan. And very ambitious. In general, the share of renewable energy pretended for 2030 is 35%. But what is important is when we analyze the articles of this draft law, for example, Article 13 and Article 14, especially mention hydrogen and alternative fuels. In particular, they explain that there should be a specific promotion in all this period, from now till 2030, promoting biomethane, hydrogen, and alternative synthetic fuels 100% renewable. That's explicitly in the new draft law to be discussed and approved by the Parliament. And there are also important things like this should be funded by the current natural gas sector. That's another important sentence. And the second thing is that 2040 is apparently now under discussion as the year that all passenger light commercial vehicles should be zero emissions, zero direct emissions. So this means even hybrid cars. And this is not only a discussion in Spain, but as you probably know, other countries like Denmark, like Germany, even France, and others are discussing this. This is coming now, this kind of discussion. So this is a big challenge, because if we analyze our country and our recent distribution of primary energy consumption, you see that transport is covered at present. Only 5% of our consumption for transport has a renewable origin. So it's probably the sector where we are farther away to achieve the current commitments for 2030 and 2040. So that's why apparently recent news are quite promising in terms of potential support from administration and authorities to alternative fuels. But the reality is, or the question is, how, if this happens, how ready we are to respond to this really 100% renewable. And of course, you always have electrolysis, and you have power to hydrogen, power to fuels. In the case of solar thermochemical, everything is quite attractive. But there are a number of issues here summarized that are related to materials, that are related to chemistry, in particular chemical engineering and solar reactors. There are topics related to heat transfer, and also to the use of advanced solar technologies. So I will try at least to give my personal vision about what are the real possible bottlenecks in the next few years if we want to be ready for this revolution of alternative fuels. And first, let's talk about chemistry, and in particular reactors, because we have the experience of receivers. Okay, we know that there are a lot of improvements in the development of solar receivers, mainly for solar towers. But the reality is that when we see where we are at present with the technologies of molten salts and volumetric receivers, and volumetrics, as you saw yesterday, are still needing more progress, we are still far away from what we need at the end, because we need to work near 1,400 and 1,300 degrees C in many of these processes. So at the end, we need sooner or later to improve the use of ceramics, either fixed bed with new kind of monolithic structures, or solutions involving particle receivers, fixed in train flow or fluid ice beds. So if we dig into the literature, what we find is all this, let's say, zoo of plenty of solutions. You know, chemical engineers and chemists like to test all combinations of Mendeleev with materials. But at the end, if we try to classify, we find particles, volumetrics, double chamber, like the ones used by PSI, or tubular. And you see that most of the current knowledge is moving between the lab scale, let's say TRL3 and TRL5. So this is the reality. But 90% of the experience is on the left. So this means that still we have to be cautious when we analyze many of the, let's say, of the declarations of the promising results in some of the processes, that many of them are on the left side. So a few of them are in the pilot, let's say a few tenths of kilowatts, and only a few processes and systems are really beyond that scale. So if you want to improve or to really speed up the development of these solutions, you need first to clarify technologies, And second, to at least to have 3 steps, you need, this is our case in my institute, you need the 1 or the few kilowatt infrastructure. In our case, basically are solar simulators at small scale. Normally, when you only need 1 lamp, but a very good monitoring, because you need really to measure very well at very demanding conditions of flux and temperature. You need the second step, I would say TRL4, that we also are trying, and you know that many of the solar chemistry researchers now are developing their own solar simulators. Probably is the largest community in solar simulators at this level is the community of chemistry and materials testing, because at the end is the size where you can really pass from the material problem to the heat transfer problem in the microreactor. And finally, you need the solar tower system, which is also a very special system. So I will try to summarize in my presentation very quickly my vision of the problems in the 3 steps. And the problem regarding the reactors is that most of them have pros and cons. The easiest way to work, for sure, developing solutions is to work on fixed materials. This is the easiest way. But the problem in most of the cases is, in that case, the temperature. It's very difficult to control the temperature inside. You will see some examples. And the operation is easy, but at the end, you never have a clear understanding about the real conditions you are working inside the reaction zone. In the case of other solutions like rotating, for example, you can improve, you have, you be more versatile, for example, controlling the residence time, etc. But most of them are tricky to operate, very tricky to operate. Material sticks to the walls. You have a lot of problems because you have to rotate the system, but at the same time, you have to have a airtight system. So that's not simple when you are working at more than 1000 degrees C. And finally, apparently is the ultimate solution, and the community is more and more moving now to particle receivers, because you can guarantee more homogeneous conditions, better heat transfer, but it's extremely sensitive to the particle properties. In some cases, believe me, it's a real nightmare to control the conditions of irradiation and temperature and fluid dynamics of the process, because just depending on the geometry of the particles, the density, etc., everything changes dramatically. So, for example, in my institute, we had a 4-year regional problem in project, involving a number of institutions and companies, and you see a portfolio of small reactors that are really needed to check all these situations. What is, let's say, at the present time, in my opinion, the benchmark, the state of the art is this experience reported by ETH Zurich in the Solar Jet project, funded by the European Commission, and the testing with this kind of material, foam material with Syria. Syria is a nice guy because the chemistry is simple, only 2 oxidation states, and the material has very nice oxygen diffusion. So they reported 5.2% efficiency solar to fuel, solar inlet to the reactor to syngas. So let's say for our community, this is today, let's say, the KPI, the key performance indicator. They also have the largest demonstration in terms of number of cycles. Here you see the simultaneous splitting in a 4 kilowatt thermal solar simulator, TRL4. And you see that almost 300 redox cycles could be demonstrated. So that's why today more and more Syria, even though has many limitations, is becoming, like in the case of photocatalysis titanium dioxide, in the case of high temperature chemistry, we need to have a reference, and Syria is becoming more and more the reference for everyone to compare. But the second problem is the heat transfer. Just to show you an example. Oh, sorry. Okay, no sound. By some reason. Okay, I wanted to show you an example here of how even for small sizes, yeah, because there was a video, a small video here. Maybe there is a problem. So I wanted to show you a small example of how for all these experiences in reactors, it's extremely difficult sometimes to understand the results you obtain if you do not have a very, very detailed analysis of the heat transfer. So even in these kind of experiments with a small reactor and like this one of few centimeters aperture, when you analyze the performance, let me show, here it is. If you analyze the performance, for example, of the sample that is in the left side in 0.3, and we illuminate with our reactor, you may see that when we see the distribution of temperatures inside the reactor, in only few seconds, you have a very high, sudden distribution of temperatures, but in some cases, the distribution of temperature is propagating in a different way than the chemistry you see. So sometimes it's not easy to understand the results and the kinetics, like in this example here. And when you see the production of hydrogen, for example, the only explanation to really understand the kinetics is that you have a good understanding of the heat transfer in the process. Solutions for this? Well, in some cases, this is the Niigata University approach, is to replace this fixed bed by fluidized beds, but they are also in an early stage of development. Probably this is one of the most developed solutions. It's a 30 kilowatt fluidized bed reactor, and they are planning to make soon a 30 kilowatt system South Japan. And the problem in all these cases is not only the heat transfer and the understanding of the chemistry, but also the materials. I am going to very quickly show you some of the problems that you need to very clearly clarify for the selection of your material. One of them is the temperature. For example, if you see manganese oxide, one of the typical examples, just only 50 degrees between the left and the right side determine the cyclability or not of the system, because it's very sensitive to temperature delta T. So this means that if you have for this specific material the correct operation temperatures, you can guarantee, you can see at the bottom, a very good cyclability. But it's extremely sensitive in many cases. Second problem is shaping. You have to shape the material. Most of the times you get it on powder, but the powder is not the good properties. So you have, for example, for rotary kilns, you have to produce pellets. And this is an example of good pellets that we produce with manganese oxide. But the problem is after a number of cycles, you see the two graphs and the size of the particle, and you see that there is an attrition, and you are losing at the end the size of the material. Very quickly, I go to the cerium oxide, has a similar problem. When you obtain this material and you analyze it, crystallographically, the morphology is very different to spheres. So it's not an easy material if you want to handle, for example, in a fluidized bed. So in our case, we could demonstrate a good production of hydrogen, but in the fixed bed, but very affected in some cases for the illumination. So you need to control, you see the production of hydrogen and the illumination you need to produce, and sometimes you need short periods of illumination continuously in fixed bed, because otherwise you can damage the material and avoid cyclability. So in other solutions, you go to macroscopic shaping. This is a typical solution, very easy to conduct, making impregnation of some materials like acrylics, foams, or polyurethane. And well, at the end, to summarize all these material solutions, we are moving always in this kind of graph where you have the temperature and the efficiency, and most of the efforts in the materials are trying to move from the complete stoichiometric oxidation reaction to the non-stoichiometric one on the left. You can reduce temperatures using, for example, mixed oxides or LS6, which is perovskite. So at the end, that's basically the idea or the development of materials. So I think I am running more or less out of time. I wanted only to finish my presentation referring to the last point, which is the high demand on the temperatures. So let me go directly to the kind of problem. It's only 2 slides to show you the final problem is regarding also the situation of the solar field. This is using a publication from Akiva Segal, where they did an analysis of efficiency of heliostat fields versus temperature. And you see marked there the typical state-of-the-art plant and a typical thermochemical process where you have to go to this high temperature. So you need very, very compact fields to reach these very, very high temperatures. So you need to change completely the solution of layout design. This is what we are doing, in fact, in our project in sand to liquid. So with compact fields, more than 40%, you really can run very high concentrations. We are at this moment in the sand to liquid project testing a 50 kilowatt reactor with this temperature. And here you see exactly the conditions we are technically running in this test, where this is marked in the center, the aperture of the reactor, and you see that we are reaching peaks of almost 4,000 tons to have a high efficiency in the process. So with these conditions of work, which is testing right now, we expect to move this 5% KPI to 8% in 1 year. That's everything. Sorry for taking more time than expected. Thank you.
For 1 or 2 questions, and I will also say that I would like to hear questions, because not a lot of consideration, etc. Not the presentation, but the question.
Yeah. Well, should I? Okay, good. Well, thank you very much, Manuel. It was a brilliant presentation. You described a very interesting state of the art of all which is going on. You know, if the ultimate goal of this kind of studies is to make an industry, I mean, to produce fuels, to produce materials out of the concentrated solar energy, I am wondering whether behind each one of the projects that you have already presented, is there the kind of pre-design of a 50 megawatt plant? So which is, you know, we are dealing with high temperatures, sometimes with high pressures, sometimes with requirements of homogeneity of the cavities or reactors. And the question is, it is feasible, or is, I mean, before starting these research lines, if the goal is to produce it industrially, shouldn't be a kind of go or no go to see whether it is feasible to think of a 10, 50 megawatt factory for this type of things? Because I think some things looks very nice at the laboratory, but I mean,
yes. Yeah. In fact, I fully agree with you, Luis. In fact, in my introduction, this is what I wanted to really stress, is that sometimes people are very optimistic presenting results, presenting solutions, but in most of the, probably most of the solutions implemented at the TRL 3 or 4 are useless. I mean, they are not scalable. So they are very interesting to learn about the process, etc. And in most of the projects, you know, they are scaling up. For example, in our project Sand to liquid, there is a specific task dedicated. Abengoa is involved, in fact, in the DLR and some partners discussing how to scale up this kind of solution. And scaling up is not clear. In fact, most of the current solutions involving fixed bed reactors, for example, are difficult to scale up beyond a few megawatts thermal. I personally think that more than 10 megawatts thermal is difficult to imagine. And in most of the other solutions, still I don't think it's a clear vision how the final plants could look like.
Is another question here.
Cyprus. I think an obvious question, sorry? Yeah. Yes. Yes, thank you very much for your interesting talk, first of all. My question is, if somebody wants to do this an industrial technology, then we're talking about long-term stability of this, of whatever kind of materials you want to use. So somebody probably would expect to see from your research some stability results. For example, in the case of Syria-based materials in the splitting of water to produce hydrogen. What is the stability in terms of days or months? Have you run such a long-term?
Well, normally we express on cycles, not on months or number of cycles. Typically, for example, in
why? Because I can see a continuous operation in a real practice. Why cycles?
Because in this kind of processes, you cycle every 20 minutes. So normally you make a cycle every hour or every 45 minutes.
Because
so typically in one day.
Because the Syria.
Yeah, exactly.
Case, and then you have to regenerate it. In some
Syria,
sense.
even in the fluidized bed reactors,
it
needs about 20 minutes, something like that.
Do you think is that doable for industrial application? This cycling every half an hour, for example. Do you know any industrial reactor?
This is one of the discussions in the process. Normally, in this kind of cycles, for example, in this kind of solutions, in some projects like sand to liquid or hydrosol, there are a number of reactors, and what you are doing is charging and discharging. So if you see, we have two cavities. We are illuminating one of them on the left, and on the right side, the other reactor is cooling down. So the oxidation step is taken with no sun, no heating. It's exothermal. So during this period, you are illuminating or putting your energy in another reactor, and you are switching all the time.
Just a short one, if I can ask about the Syria. Why you said Syria is the basic material? Because, of course, here we're interested to utilize the redox, the bond strength of oxygen with cerium. There are so nice materials today used, for example, in three-way catalysis, Syria zirconia, doped Syria actually, which much higher.
We are doping with zirconia and with iron. What I mean is that for the community, normally at the end you need a material to compare. I mean, there are at least 12, 20 groups working with Syria, and normally you need something like a reference material for comparison. So today, Syria is becoming, let's say, the reference material for everyone, like the benchmark. But I didn't say that this is the best option. In fact, Syria is not the final solution.
Okay, thank you.
Jack, you have
I guess my question is similar to the first one. It's more of a practical question, and that is, has there been any systems analysis to look at how if this makes sense on an industrial scale? In other words, there are huge quantities of liquid fuels that are used in the world, and if we're going to limit ourselves to where you have to have a concentrating solar flux, you need high concentration. You got to move the water or biomass or whatever your source material is to the desert location, and then you're going through a small area where concentrated flux occurs.
Yeah.
I see that as a bottleneck. So has this analysis been done to look at
environmental science technology?
Shows that it's practical?
Yeah, we did the company Bauhaus, Lufthansa in Munich is doing this part of the analysis. Our project is, the final target is to produce kerosene for airplanes. And we take into account the water with desalination, for Morocco case, for example, the consumption of electricity, etc. And you see that here in the conventional jet fuel cost, and more or less the conclusion is that we are twice as much double cost that the current price of the kerosene. And one of the main aspects of cost is the CO2. CO2 origin, because CO2 is an important demand. There is a huge demand of CO2 in the process, and this is an important element of cost.
And replacing jet fuel, of course, would make a big difference. I mean, that's not an easy sector to address in terms of carbon emissions. So
it's a perfect.
Yeah, it seems like a good thing to focus on.
Yeah.
Okay, thank you.
The last
Quick
question.
question. You mentioned that you need very high flux. Are you using any second stage concentration at all?
In this testing, we are not using second stage, but for the scaling up plant they are analyzing, there are. We are not using because in principle it's not needed. For this concentration you saw, it's not needed.
Well, thank you very much, Manuel.